Welcome to the Wastewater Treatment Certification Training webinar series. Today we will look at Chapter 2, KPDES Permitting, and the presenter today is John Walker. The Clean Water Act was a federal statute that established that any wastewater facility that discharged from a point source must have a permit. These discharge permits are issued by the Division of Water and are termed Kentucky Pollutant Discharge Elimination System Permits, or KPDES permits. What these permits allow you to do is discharge certain levels of pollutants into the bodies of water of the Commonwealth of Kentucky and set limits to what you can discharge into those receiving waters. So in a permit, what this will tell you is what pollutants can you discharge into the source waters, what those limits are in terms of concentration, how much can be discharged either on a daily or a monthly basis, the sampling frequency for each of these pollutants or parameters, and the collection method that you will have to use for each of these pollutants or parameters. When I mean parameter, I'm talking about things like temperature and pH and dissolved oxygen, and pollutants are things like organic matter, nitrogen, phosphorus, chlorine, etc., etc. The permit also requires a reporting frequency for the results, which we will look at in a little later slide. And under certain conditions, the permit is a license, allows the facility to discharge a certain amount of these pollutants into the receiving waters. So it sets the rules for what you can and cannot do. The Clean Water Act and the Safe Drinking Water Act and other federal acts basically were intended to preserve not just the waters of the Commonwealth, but the waters of the United States for drinking water supplies, to allow the natural environment, the fish and other wildlife to survive, provides for safe uses of water for agriculture and recreation, and has some ways to prevent and to help control what pollutants are added to the water. And so to make this work, there has to be a means of enforcement within that permit. So what is a pollutant? Well, according to the Clean Water Act, any type of waste, including heat, that's discharged into the receiving waters of the Commonwealth in terms of Kentucky is a pollutant. And in Kentucky, we have defined it a little more specifically, and it's anything that alters the properties of the water that can be detrimental to either public health or to aquatic life, whether that's in the rivers, lakes, reservoirs, or even as it gets into the sea. And so any change in the physical, the temperature, the chemical constituents of the water, the biological levels of the water, or even radioactivity is considered a pollutant. So there are three different ways which we can classify pollutants. Ones that we call conventional, these are the ones that we test for. These are the ones that you will have limits for example, BOD, which is the organic matter in the water. Total suspended solids, this is the turbidity in the water. Fecal coliforms, these are the organisms that could make you sick, and pH. Then we have toxic pollutants. These are the heavy metals, some synthetic organic chemicals, and substances such as benzene. And then the non-conventional ones, these are really something that doesn't fall either in conventional or toxic. These are ammonia and phosphorus and chlorine. And we will look at each of these in some detail later on. As you put a permit together, there needs to be certain components of these, certain elements of these in order to get the permit approved. Everything has to have a front page with the name and the location of your plant, who will be operating the plant that the permit will be issued to, a statement that says that you can discharge into the receiving waters of the Commonwealth, and where those locations of discharge are going to be. Also in the permit is going to be the limits of what you can put into the receiving waters of the Commonwealth. And these limits are really going to be based on water quality standards and what applicable technologies you have available to make sure that you can remove them from the wastewater stream before discharge. There has to be monitoring and reporting requirements so we can characterize what's in the waste stream and what's in the discharge and receiving waters, and an ability to check that the treatments are effective and that you are complying with the permits, with the conditions of the permit. There are standard conditions. These apply to all KPDES permits, regardless of the type of plant, the size of plant, the location of plant. But as with everything else that goes on, there are special conditions that will apply to your permit that might require additional monitoring, some extra studies, a change in the compliance, and how you will manage and operate your plant. One of the processes that you have to do every month is to fill out what's known as a discharge monitoring report, or DMR. And in this report, you will use that to essentially determine what was in your waste stream and what went into the receiving waters of the Commonwealth. This is also a way that you can evaluate how efficient your wastewater treatment process is, and because it's data, it will help determine whether you are complying with the conditions of the permit. This is now online, and this is an example of what you may have to fill out. Here is the information, the names of the parameter. Here you see pH. Here you see suspended solids, phosphorus, iron, aluminium, and so on and so forth. This is where you would put the information that you're going to receive for what those parameters are, the frequency of analysis, and what the sample type was. So when you sample for analysis of the waters that you're going to discharge, there are some things that are going to be important to understand for each parameter or pollutant. whether you collect it in plastic or glass. If you want to go back to the previous slide, you will see that it will determine which you can use. There's something that we call holding time, and this is the maximum amount of time to complete the testing. This does not mean that you hold it for that time before you send it to test, but it is the maximum amount of time to complete the testing. And the EPA has a lot of documentation on this that you can look for and download to tell you exactly what you need to do. All metals that you're going to test for should be contained in glass, not plastic, and you will preserve those with nitric acid to a pH of less than 2. The only exceptions to these for metals is chromium-6 and mercury, and if you have to sample for those, you will preserve those and treat them differently. And again, those instructions and those requirements are provided by the EPA. So as you sample, there are two different ways of sampling: grab samples and composite samples. And in grab samples, there are, again, divided into two groups: things that you test instantaneously, and those that are going to be preserved for testing later in a lab. So what distinguishes a grab sample from a composite sample? Well, grab samples are collected at one moment in time. You sort of grab the sample out of the water, and that's the sample. It is only going to give you information on the conditions of the water at the time the sample was taken. So if you were to take it 20 minutes later, you will probably get or may get a slightly different result. So you can't, once you take a grab sample, you can't say, well, that's the sample of the water for the rest of the day. Samples for grab samples can be preserved, and fecal coliforms are a really good example of how you would take a grab sample, cool it down, and then analyze it within a certain number of hours. But a lot of grab samples you will take as instantaneous samples, and these are the ones that you're going to analyze straight away, usually with a specific meter, such as a pH meter, dissolved oxygen, you recording the temperature, and depending on where you're taking the samples, the chlorine levels. So chlorine, so you're not discharging chlorine into the receiving waters of the Commonwealth. So grab samples collected at one moment in time. They're only going to tell you what's going on at that point in time, not earlier or later. You're either going to preserve them and analyze them later, usually in a lab, or you're going to have an immediate response reading of the sample, the water sample, as you take it. Composite samples, these are where you will collect multiple samples, usually equal volumes, 100 mils minimum, and depending on the requirements of the parameter or pollutant and the permit, usually you will collect these at certain intervals every 15 minutes over a day's time, 24-hour period. And then you're going to pull all those samples together, and that is going to be what you will get tested. There are two types of composite samples, one that we call flow proportional, and that is a certain amount of your flow you will collect. So as your flow changes, the amount of sample that you collect will change. If flow goes up, you'll collect more. If it goes down, you'll collect less. and you'll collect these at a fixed time depending on the flow. And then you have time aggregated samples, which are basically just collecting a certain volume, say every 15 minutes. So the sample that you collect when you test it will reflect the average quality of that water over the sampling period. So why is a composite sample important? Why don't you just take multiple grab samples? Well, if you look at the flow through a water treatment plant, we start here at midnight. It's really low. Everybody's gone to bed. Well, most people have gone to bed. Then as it gets in the morning, it starts to go up. Just around lunchtime, it has a peak. And then in the evening, water flow increases. So if you were to take just your sample here, or even here, you would get a very different result than if you took samples over a period of time, say here, and added it to here, to here, to here, and so on and so forth. So composite samples give you a good idea of what's going on throughout the day of the way that the water is being treated. Whether it's a sample for testing later as a grab sample or a composite sample, all samples should be labeled with at least this information. So the number of the permit, KPDS number, what the sample name or its ID. I don't know how many of you use a system with barcodes or QR codes, but that would be a useful thing to look for. What you're going to test, what the analysis will be performed on that sample. Who is requesting the test, the date, the time the sample was collected if it's a grab sample, and who collected it. So if any of that information is missing, you're not going to have enough information later on. And if the sample gets missing or lost or misread, you're not going to get the data you need. So what are we looking at in a permit? What does the permit check for or control as you treat the water? So in domestic wastewater permits, you're going to pretty much look at everything that's very similar because what goes down the toilet and the sink isn't going to change dramatically from one part of the state to the other. However, if it's an industrial wastewater permit, it is going to change, and what you are going to be asked to test for will depend on what your manufacturing process is, on what waste will be produced. And we'll look at this later on in the presentation. Sometimes there are special monitoring requirements. There is something called whole effluent toxicity. This is where basically you take the whole effluent and you look to see the aggregate, the total effect that sample will have on essentially aquatic life. Sometimes we use little water fleas or fish, and we add the water to that and see whether they survive or not. And this is really an issue for industrial flows, where we know that there are certain things in that waste because of the manufacturing process of the industry. But for domestic wastewater parameters, this is a list of the next couple of slides. We are going to look for total suspended solids, biochemical oxygen demand. This is the amount of organic material in wastewater that bacteria can use. We will look for ammonia and phosphorus and metals. We will look at flow to make sure we are not overloading the plant. Because it's wastewater, we are really going to look for fecal coliforms as indicator species and E. coli to make sure that there is no potential for disease, and then other things such as dissolved oxygen, so we know that there's enough oxygen in the water to treat the wastewater, or there's enough oxygen as it's discharged into the receiving waters so that the fish and plants can survive. Of course, pH, we don't want to have too low or too high a pH as we discharge the waste, and we want to make sure that there's not too much chlorine going into the receiving waters of the Commonwealth. Next few slides look at what is in raw wastewater as it comes into the plant. You'll notice that 99.9% of wastewater is actually water. There's very little solids in it. 0.1% is solids. Of that 1%, a little less is dissolved solids, suspended solids, and then down here we've got even smaller amounts of solids that we can call settlable or colloidal. Colloidal are solids that, suspended solids that don't easily settle. So total suspended solids are solids that do not pass through a filter. They are not dissolved, and as shown in the previous slide, they really don't make up a huge percentage of domestic wastewater, 0.1%. The average influent range that we might encounter for domestic wastewater is between 180 and 300 milligrams per liter. Your mileage may vary depending on where your waste is coming from, but there is a way of calculating how much might be excreted per person per day, and the number that has been calculated is 0.2 pounds of total suspended solids that each person per day will send to the wastewater treatment plant. The sample collection for TSS is a 24-hour composite sample, again because the amount of waste coming through is going to vary depending on the time of day. You will check the influent and the effluent to see what the levels are, because the aim is to remove 85% of the influent total suspended solids during the treatment process. Doesn't matter for TSS whether you save in plastic or glass, but the sample must be cooled to 6 degrees centigrade, and you have 7 days to get that sample tested. Of course, you're not going to wait until day 7 to get it tested. You're going to get it tested before that, but you have up to 7 days. We're going to do a little bit of math now. And those of you who have taken this class or this series before will be very familiar with this pie chart, this pie diagram for the pounds formula. And this is something that you will have to be very familiar with as you take this class and take the test. The purpose of this is to determine really two things: the amount of pounds of material that is in the wastewater system, or the concentration of something that's in the wastewater system, either as a sample or a dosage. So you will see in this bottom formula, this is either a dosage or a concentration. So let's look at this diagram in a little more detail. So pounds per day equals million gallons per day times 8.34, which is the weight of 1 pound of water, times the concentration in milligrams per liter. And the reason why we measure this in milligrams per day is this is 1 milligram is 1/1,000,000th of a liter. You can look at this formula. This same pie chart will allow you to develop, and this formula where the concentration or dose equals the pounds divided by million gallons per day times 8.34. And if you look at this formula, you can look at this line here as either a dividing line, like you see it here, or an equal sign, like you see it here. So pounds per day equals million gallons per day, or flow or volume, times, those diagonal lines can be the multiplication system, 8.34 times milligrams per liter. And if we look at milligrams per liter, you can put your thumb or finger over this. There's your equal sign. So your dose or your concentration equals pounds per day divided by million gallons per day times 8.34. We will be going over this many times, so it's on your formula sheet as well, and we'll go on to the next slide, because we're going to now do a little bit of math. So in your manual, in the math study guide, and in the test, you will see questions like this. So the influent concentration of total suspended solids to a 2 million gallon per day oxidation ditch is 189 milligrams per liter. The BOD influent concentration is 154 milligrams per liter, and the influent flow is 1.5 million gallons per day. The question we want you to ask is how many pounds of TSS enter this plant daily. Now, look at the information in this slide, in this question, and look what the question is asking you. Concentration of TSS and the BOD influent concentration. Here is the formula you're going to need. We're looking for pounds, we need million gallons per day, and we need a concentration. So the influent flow, not the size of the plant, the influent flow is 1.5 million gallons per day, and that's the number that you need here. Here's your 8.34, your pounds per 1 gallon of water, and we're looking at TSS, and the question tells us that the concentration of TSS is 189 milligrams per liter. And if we put all those numbers in our calculator and we multiply them all together, we should get the answer of 2,364.4 pounds of total suspended solids. So just be familiar with the fact that a question like this, whether it's in the manual, the math study guide, and certainly the test, to know which information you need to ignore and which information you need to enter into the formulas. So here is an example of one that you will do. We will given you the answers as you would see them on a test. So the effluent flow from a 0.75 million gallon per day oxidation ditch is 0.44 million gallons per day, and the concentration is 13 milligrams per liter. How many pounds of TSS are in the effluent? So again, we have two volumes here, two flows here, but we know that we're more interested in the flow rather than the size of the oxidation ditch. Another piece of information to be very well aware of is what comes into a plant in terms of flow has to leave a plant in terms of flow. So although we haven't given you an influent flow, the fact that we've given you the effluent flow of 0.44 million gallons per day is what you will use. So I'm going to give you as much time as you like to work this problem through. So if you want to pause the recording, work it out, and I'll show you the answer. I'm going to wait here about 20 seconds, and then I'm going to put the answer up. So take your time. When you're ready, you can restart the recording. Okay, the answer is A, 47.7 pounds. So let's see on the next slide how we came up with that answer. Here is the formula that you will need. Here is your flow, 8.34 times the concentration. And if we put the numbers in from that question, 0.44, remember this is the flow, not the volume of the ditch. 8.34 is pounds of 1 gallon of water, and here was our concentration at 13 milligrams per liter. And we should get, or you should get 47.7 pounds. So here is where we're using that same pounds formula, but we're now looking for concentration rather than pounds. And here we have the question mark here in concentration. So the question asks us that if the organic load, the BOD load was 3,678.5 pounds, with an influent flow of 1.9 million gallons per day. What is the concentration? There is the formula. You can see concentration equals pounds divided by million gallons per day times 8.34. Note that here is the flow of 1.9, not 2.5 million gallons per day, which is the volume of the plant. And if we look at those numbers, we get 232.1 milligrams per liter. So here is one that you can do yourself. Again, after we've gone through this, I'm going to wait about 20 seconds, and you can stop the recording. And when you've finished it in the time that you need, you can restart and we'll look at the answers. So the effluent BOD loading at a 0.5 million gallon per day wastewater plant is 12 pounds. and the flow is 320,000 gallons per day. What is the effluent BOD concentration? Now again, what we've done is we've changed this up a little bit, and we've given you this flow not in million gallons per day, but in gallons per day. So you're going to have to convert this into million gallons per day before you can do the solve the problem. So again, I'm going to give you some time to do this. So pause the presentation, take the time you need, and then you can restart it. So the answer is 4.5 milligrams per liter. And in the next slide, we will see how we got that answer. Here is your pounds formula pie chart. Concentration is pounds of flow times 8.34. We put all the numbers in. We have to do that conversion from gallons per day to million gallons per day. And you either divide this by a million or you move the decimal point 6 places. So here it starts 1, 2, 3, 4, 5, 6, which is where we get the 0.32 million gallons per day from. So we put those numbers in, and there we get our answer of 4.5 milligrams per liter. So let's go back and look at some of those parameters that we have to test for in the water, both coming in and leaving the plant. So biochemical oxygen demand, BOD5. This really is a way of measuring how much organic material is in the wastewater. The science behind this goes back over 100 years when Britain was trying to clean up its rivers so that people weren't dying and the smell wasn't too bad. And essentially, BOD5 measures the food that the bacteria can use during the treatment of wastewater. On average, the range of influent BOD in the manual and for the purposes of this class is 160 to 280 milligrams per liter. Your mileage may vary out of that sometimes, but again, we can look and say essentially that every person per day is going to add 0.17 pounds of BOD into their toilets and sinks, and like total suspended solids, 85% of this BOD must be removed in the treatment process before discharging into the waters of the Commonwealth. We'll look at these numbers a little later when we talk about population equivalents. So the sample collection for BOD, like TSS, is a composite sample. Again, you're going to collect the water coming in and the water as it's being discharged. Plastic or glass are acceptable. Again, you're going to cool to 6 degrees centigrade, but the holding time is only 48 hours or 2 days. But again, once you've sampled these, you're probably going to test it quicker than that. So how do we calculate BOD? Well, what we do is we take a sample of the influent and we add it to this bottle. Depending on the method you use, you might add some bacteria to this, and you're going to measure the initial level of oxygen, dissolved oxygen in the sample, and then after 5 days, the final level of oxygen. And the assumption is that as the bacteria break down the organic material, they are going to use oxygen. So the initial level of oxygen is going to be higher, hopefully higher than the end one, and that's going to give you an estimate of the organic material present in that sample. So we take the initial level of oxygen and we subtract the final level of oxygen from that. And because we're going to add a certain sample to this bottle, and then there's a volume of the bottle, we have to account for that. So we take those levels of oxygen, multiply that by the volume of the bottle, and divide that by the sample volume, and we should get our answer of BOD. So the math problem, if we have a 15 ml sample, and initially it was 7.4 milligrams per liter of dissolved oxygen, we incubate that for 5 days. The volume of the sample bottle was 300 mils, and the final DO was 3.9. We can use those numbers to calculate the BOD. So the initial dissolved oxygen was 7.4. The final dissolved oxygen was 3.9. The volume of the test bottle, the BOD bottle, was 300 mils, and the sample volume was 15 mils. And if we put all those numbers into the formula, it should look something like this. If you want to calculate this before I carry on, then just pause and work it out, but I'm just going to carry on for this one, and you're going to have another example to do by yourself later. So you end up with 3.5 times 300 mils divided by 15 mils, which gives you an BOD of about 70 milligrams per liter. So here is one that you can do yourself. The initial DO of a 25 ml sample was 7.1. 5 days later, the dissolved oxygen level was 4.1. The sample of the test sample was 300 ml bottle. And again, take your time to work this out. Pause the recording and then restart when you think you've got the answer. Again, I'm going to, in a few seconds, I will carry on. I will show the answer. And then on the next slide, we'll show you how we got that result. So the answer is 36 milligrams per liter of BOD5 in the sample. So here is the formula. Those are the numbers that we had. Initial DO of 7.1, final DO of 4.1. Notice from the other problem we worked out, we have a slightly different sample volume. And if we put all those numbers together, we should get our 36 milligrams per liter. The next bit of math that we're going to run through is percent removal. If you remember, mentioned that both TSS and BOD, you have to remove at least 85% of that between what comes in and what leaves. So this is how we're going to calculate that percent removal. And so we figure out what the concentration is in the influent, subtract what's in the effluent, divide that by the influent. Because we're looking for a percentage, we multiply by 100, and that gives the percent removal. This is one of the few calculations that you're going to do where there are no units. As long as the units are the same, you're measuring in milligrams per liter, units don't matter. So here we'll just run through this. The influent concentration of BOD is 51.6 milligrams per liter, and the effluent is 3.12 milligrams per liter. Have we reached the minimum of 85% removal? Well, let's look at how we put those numbers into this formula. Influent minus effluent divided by influent and multiplied by 100. There's the numbers. We get 93.95% removal. So for this example, we have removed greater than 85% of the BOD. We're looking good. So some of the other parameters that we will have to test for is ammonia, or this is another way of saying nitrogen. We can either look at this as nitrogen as ammonia. Ammonia is NH3, and the range in domestic wastewater is anywhere between 25 to 30 milligrams per liter. Some of that will be organic. A lot of organic material like protein has nitrogen in it. And so that some of that is going to be lower, so 15 to 20 milligrams per liter. And there is a specific test called the Kadal nitrogen, which is basically the sum of both of those together. And based on studies that have been done, and this is part of the design of maybe some wastewater plants, every day it's estimated that each person will flush down the toilet or the sink about 0.02 pounds of nitrogen per day. When you sample for ammonia and nitrogen, glass is preferred, although you can use plastic if you have to. These are preserved by adding sulfuric acid to lower the pH less than 2. Again, things need to be cooled on ice to at least 6 degrees centigrade, and there is a 28-day holding time. Phosphorus, again, we are able to determine or have an idea of how much phosphorus each person flushes down into the sewer system each day, and it is 0.0048 pounds of phosphorus. This can be organic. Phosphorus is found in lots of organic material, but there is a lot of inorganic phosphorus because of the use of fertilizers, and or it's less now, but there used to be phosphorus in detergents and dishwasher liquids. I think they've taken a lot of those out. So the range is 5 to 20 milligrams per liter. And again, maybe a third of that is organic. The ways that you can remove phosphorus is chemical or biological, or use a combination of both. And again, you are really not necessarily needing to test the influent, but you certainly will need to test the effluent and record the numbers. At this point, I don't think there is a limit on phosphorus, although it might be in the works. And depending on your facility and the wastewater you collect, you might not even have to treat for phosphorus. But your mileage may vary, but remember that it will be in your permit. So again, composite sampling is usually the sampling we use, but again, your permit might require you to do otherwise. Preservation is very similar to nitrogen. Add sulfuric acid to pH less than 2, cool to 6 degrees centigrade, and you can hold it for up to 28 days. And again, glass or plastic sampling containers are both okay to use. So here's a little bit of basic math. There won't be necessarily a formula for this anywhere on your formula sheet, but we'll walk you through how to solve these problems. So your daily flow into a 7 million gallon per day water plant is 5.5 million gallons per day. There are 45,000 people in this community. How many pounds of phosphorus will be in that influent daily? So we know from the previous slides that each person on average contributes 0.0048 pounds per day. So long as we know how many people, we can multiply that by 0.0048, and there should be somewhere in the region of 216 pounds of phosphorus entering that wastewater treatment plant. Note that we didn't use the pi formula, the pounds formula. We didn't need to know the volume of the plant or the flow of the influent. So again, this is just a very simple basic math problem. Won't have a formula on the formula sheet, but be aware of how to solve these questions, both in the manual, the study guide, and the test. Going on to the next set of parameters that you will test in the water plant, we're going to talk a little bit about metals. And I'm going to introduce you to two terms, conservative and non-conservative. This has nothing to do with the political leanings of the metal. Essentially, a conservative pollutant is something that is conserved throughout the process, i.e., it is not degraded or given off into the atmosphere during the treatment process. Non-conservative pollutants are degraded, or they are gassed out into the atmosphere during the treatment process. So metals are conservative pollutants. Don't worry about the numbers on this slide, but I just want to point out the common metals that are usually found or tested for in wastewater treatment. So copper and lead, that's in there because of the pipes that are used in plumbing. Depending on if you've got some industrial processes in your area, you're going to have cadmium and chromium, cyanide, maybe some mercury and arsenic and nickel. A lot of these are from electroplating plants. Mercury used to come a lot from coal-fired power plants and then settle into rivers and lakes. But with a reduction of that, this is hopefully getting a little lower. And you'll notice that the levels of this are really low because mercury is really, really toxic. So all metals, with the exception of mercury and chromium-6, are preserved with nitric acid to a pH of less than 2. Mercury and chromium-6 are dealt with very differently, and if you have to test for those, you will have your own protocols for preserving those. You can use either glass or plastic. Again, you will cool all samples to about 6 degrees centigrade, and there is a holding time of about 28 days. But again, you'll probably have these tested much more speedily than that. We have to measure flow. This is just a report. Again, you have a design capacity for your plant, but your flow will vary, especially following rain events, because our collection system, our sewage system isn't perfect. You will record these in million gallons per day. Any flow meters that you have, and if you're going to discharge greater than 50,000 gallons per day, you are going to need a flow meter, and that flow meter has to be accurate to plus or minus 10%. Again, there is an estimate based on the amount of people that you have, the number of people that you have in your area, and that estimated flows are 100 gallons per day per person. That is all the water that goes down the sink, the toilet, the shower, the washing machine, etc., etc. We have to test for potential pathogens in the water. This is an example of biological sampling. And we are going to test for fecal coliforms because they are indicators of human waste or even animal waste. And very specifically for E. coli, if we find E. coli, that is not a good thing. They have the capacity to cause disease. They are potential pathogens, and the limits for fecal coliforms are 200 colonies per 100 mils as an average, and as a daily maximum 400 colonies per 100 mils. And what each of these colonies is expected to represent a single bacteria. The limits for E. coli are lower, 130 and 240 colonies as the daily maximum. And this is an example of what we call a Petri dish with agar in it. I think Americans call it Petri dish and agar. So I apologize for the accent there, guys. But when you plate a sample on this, the bacteria grow on the agar, and depending on the chemicals that you can put into this agar, you can distinguish one type of organism from another. And the red colonies are coliforms, and the violet ones, like this one here, are E. coli. You will see some that seem very beige. They're neither. And so you count these, and if you took your time to count them, and you can figure out whether this passes the limits or not. I will tell you now that it doesn't, but if you want to count them and maybe prove me wrong, then please go ahead. Anytime you test for bacteria, you've got to have a sterile container. So don't just sort of pick one off the shelf and open it up and sniff it and say, yeah, that's clean enough. It will be a grab sample from the effluent. Of course, there's no point in testing for coliforms on the effluent because it's going to be full of them. Preservation, again, you're going to cool it to 6 degrees. You have a 6-hour holding time. That is 6 hours from taking the sample until you begin to culture those bacteria. And in the sample container, anytime you take a sample for coliforms, there should be it should be sealed. If it's not sealed, don't use it. And in the bottom, there should be a little bit of white powder that is a compound called sodium thiosulfate, and that removes any chlorine from the sample so that the chlorine doesn't interfere with the growth of any bacteria that are in the sample. We're going to talk now about other parameters. Dissolved oxygen. This is going to be an instantaneous sample, and you're going to read it straight away. It's a grab sample. The meter that you're going to use should be calibrated certainly daily or before each use. The range in the plant operation is anywhere between 2 to 4 milligrams per liter, but the permit usually will require greater than 7 milligrams or greater. Again, your permit might require higher levels of DO because as the water gets discharged, that amount of oxygen is going to be necessary for bacteria and other aquatic life to survive, such as fish and insects. We're going to also need to measure pH. pH is a measure of the hydrogen ion concentration of a solution, how acid or alkaline that solution is. It's measured on a scale from 0 to 14. The permit range for effluent is usually between 6 to 9, unless the permit might require something else. And again, like dissolved oxygen, it is an instantaneous grab sample. And again, like a DO meter, pH meters need to be calibrated certainly on a daily basis, and if they're not used for a long time, before each use. This is a cartoon showing the scale of pH. pH 7 is neutral. Water that's not got anything in it will have a pH, should have a pH of close to 7. Blood is slightly more alkaline. Vinegar and tomatoes are low pHs. Lemons, hydrochloric acid, this is the stomach acid that's helping you digest your food, as a pH close to 0. On the other scale, things like drain cleaner, sodium hydroxide, or lye has a pH of 14. We're always saying, well, you know, acid's bad, but alkalis can be even worse. If you've ever got any drain cleaner on your fingers and you rub your fingers together and it feels very soapy, that's because you've just made soap with the fats in your skin. So if you ever get lye on your fingers or any body part, wash it off very quickly. Again, pH of 7 is neutral. Any pH less than 7 is acidic and has more hydrogen ions. pH is greater than 7 are basic. They have fewer hydrogen ions. The interesting thing about the pH scale is it's not linear. We call it logarithmic, in that a pH of 5 has 10 times more hydrogen ions than a pH of 6. A pH of 4 has 100 times more hydrogen ions than a pH of 6. pHs of 8 have 10 times fewer hydrogen ions than a pH of 7, and so on and so on. something I just want to make sure that you understand before we go over this. I mentioned in the previous slide, pHs greater than 7 were basic. We can also call these alkaline, but there is another term that we use in wastewater treatment called alkalinity. This is the ability of a solution to buffer acids. It prevents if acids are added, it prevents the pH from dropping very quickly. That is also called alkalinity. So be very aware of the context in which the word alkalinity is used. It can mean pH is greater than 7, but it's also a measure of the ability of that solution to not become too acidic. That ability is called buffering. Chlorine, because we don't want to be putting pathogens into the water, one of the things that you will do in a treatment plant is to disinfect the water. Chlorine is still a very useful treatment to eliminate bacteria, but it is also dangerous if it gets into the waters of the Commonwealth. So we have limits. The daily maximum is 0.019 milligrams per liter, and the monthly average can't be greater than 0.011 milligrams per liter. This is an instantaneous sample, and again, calibrate meters daily. There are two methods that are used, something called an amperometric or an electrode method. Again, you'll find this in the lab. It's not something that you will necessarily carry around with you. And the reasons why these are low is because chlorine, even at low levels of chlorine of about 0.1%, are toxic to fish. And that's the last thing we need, is to affect the wildlife in our streams and rivers significantly. This ends chapter 2, the KPDES permit, and there are two ways to contact us with either questions or comments, either by email through envhelp@ky.gov or by phone 502-782-6189. We very much recommend that if you have any questions or comments, that you please contact us. That's what we're here for, to help you understand this information and to get certified. This ends the presentation. Thank you very much.